On September 15, 1940, the Luftwaffe began a ferocious campaign targeting London. A sudden change in tactics, focusing the full might of their air force on the most heavily populated city in Great Britain. Over the course of this brutal day, over 1,100 German aircraft entered British airspace, an astonishing invasion to attack a non-strategic civilian target. However, this was all part of the Luftwaffe's plan to gain air superiority in British skies, baiting British fighter planes into the sky to face off against their German counterparts. A showdown to eliminate the Royal Air Force as a threat, to pave the way for a German amphibious invasion of Britain. On this first day of the infamous Blitz, over 1,000 aircraft on both sides tangled in the skies above London. The Luftwaffe believed the RAF were on their last legs, but that couldn't have been further from the truth. The Spitfires and Hurricanes, being manufactured in astonishing numbers, outpacing the attrition of the battle, rose to meet the challenge. The pilots of the Luftwaffe, flying the Bf-109, were astonished at the resistance they met. However, another number from this period stands out to me. Over the course of this month, the 6th Anti-Aircraft Division, covering the Thames Estuary, the main approach to London from Europe, expended over 250,000 anti-aircraft rounds in its effort to protect the citizens of London. A bewildering 1,800 rounds were needed to take down a single aircraft on this day, according to official records. These numbers are largely accepted by experts as false, with actual rounds needed much higher. Many downed German aircraft claimed by anti-aircraft crews were in fact shot down by fighters in the sky. Because of these false reports and anti-aircraft technology's ineffectiveness were the same. So, why was anti-aircraft technology during the Battle of Britain so ineffective at damaging invading planes? And how did an ingenious top-secret technology introduced in the middle of the war change the face of the battlefield forever? At the outbreak of the war, anti-aircraft technology was, for the most part, a deterrent. A weapon that became vastly more effective at lower altitudes and in turn forced enemy aircraft high above the clouds, where they themselves struggled to hit the mark. The task of accurately targeting a high-flying aircraft from the ground was an even more immense challenge. In the best-case scenario, anti-aircraft crews had a direct line of sight with their target, allowing them to estimate both altitude, bearing, and speed. This information was used to aim their barrels to a location in front of the formation's current location, an educated guess of where they would be when the shells arrived. To make this task even harder, Allied fuses had to be timed on the ground, turning a dial on a mechanically timed fuse. Calculating the time it would take for the round to reach the target in the heat of battle was difficult. These calculations needed to be incredibly accurate, allowing the anti-aircraft rounds to explode in close proximity to their target. This variable was also subject to change as pilots were instructed to change their altitude and bearing randomly to make it impossible to predict flight time and future location. This was a game of chance and, as such, relied on an incredible volume of fire to stand a chance of damaging their target. This problem needed to be solved and was high on the mind of the British as they held through the brutal storm of this bombing campaign. For anti-aircraft rounds to become vastly more effective, they needed a way to detect their target. In the era of fragile vacuum tubes, building an electronic device capable of surviving the immense 20,000 G acceleration launch out of a gun barrel was a task that was deemed impossible. Work began on radar-triggered fuses in both Britain and Germany before the war broke out, and both abandoned the idea completely for gun-launched projectiles, seeing no way to overcome the technical challenge of ruggedizing the electronics or miniaturizing them to fit into a small artillery shell fuse. However, the Americans persevered and came up with this, the VT fuse, with its ominous red vial of liquid at its core, serving a vital purpose. The challenge of finding a suitable power source for this radar transmitter was another challenge facing the engineers. Early versions of the proximity fuse utilized existing dry cell battery technology, but these came with two huge issues. their charge would fade in just 2 to 3 months, making long-term storage of these fuses impossible. And secondly, the risk of having power accidentally connect to the transmitter and receiver was far too high. A single failure point could explode an entire ammunition stockpile. For a reminder of what that looks like, this is not a nuclear bomb. This is the SS John Burke, a United States ammunition transport ship that was struck by a Japanese kamikaze bomber while transporting ammunition to the Philippines in 1944. The war in the Pacific was the driving force for the invention of the proximity fuse. The US were losing an astonishing number of ships to Japanese aerial attacks and desperately needed a better way to defend their ships with anti-aircraft fire. The solution the US National Defense Research Committee came up with to solve this issue of safely powering this device was as bizarre and unique as it was ingenious. The engineers switched to a wet cell design. This red vial contains the electrolyte of the battery. This allowed for an ingenious workaround for both problems. The liquid electrolyte was stored inside the battery, separated from the solid plates of the battery inside this vial. Underneath this glass ampule lay a breaker that contained a clever mechanism. 2 levers were pushed towards the center of the mechanism by a spring. When the round began to spin at 50,000 revolutions per minute as a result of the rifling in the gun barrel, these levers would be forced out, which released a trigger, allowing a small explosive primer to force a spiked plunger to break free and strike the glass ampule, breaking it and releasing the electrolyte into the battery. The plates of the battery were composed of thin zinc plates coated in carbon on one side, each layer separated by a plastic insulating ring, and each disc had holes punched into it to allow the electrolyte to flow and fill each layer. This glass could, of course, break with rough handling, but the electrolyte would not fill the space between the battery plates without the centrifugal force of the round forcing the liquid outwards into the surrounding plates. Other safety measures were incorporated to make absolutely sure that the chances of an accidental detonation could only happen when the round was in the air and spun at tremendous speeds. Once energized, this battery would provide power to the oscillator, which generated a continuous sine wave radio current to the transmitter. For space efficiency's sake, the antenna operated as both a transmitter and receiver. With the currents traveling through the same antenna, the fuse needed a way to differentiate between the signal sent and the signal received. For this, the engineers could turn to the Doppler effect. As the target and fuse are traveling towards each other, we can easily calculate the apparent frequency shift due to their relative velocity. Then, with some basic math, we can come up with this equation, subtracting the reflected frequency from the actual frequency. This was called the beat note. This beat note is what the fuse used to detonate the round. The amplitude of this beat signal would also grow as the round approaches the target, providing a signal that looks something like this with amplification. The fuse was tuned to explode at the optimum distance and angle away from the target by tailoring the radar sensitivity to match the fragmentation pattern of the shells. When the round approached the target, the returning radar waves would generate the necessary threshold voltage to trigger the thyrotron, a type of high-speed electrical switch. It looks a lot like a vacuum tube, but it was filled with a low-pressure gas like hydrogen. When a voltage of sufficient magnitude was passed from the amplifier to the cathode grid of the thyrotron, it would ionize the gas inside and allow current to flow to the anode through its glowing cloud of ionized atoms, completing a circuit to a capacitor that in turn would detonate the high explosive charge in the round, creating a cloud of shrapnel at the optimum distance away from the target. This whole assembly, consisting of the vividly red electrolyte capsule, the zinc-carbon battery plates, oscillator, antenna, amplifier, and thyrotron, was then inserted into the fuse body, and the cavities of the fuse were filled with a microcrystalline wax for moisture protection and, critically, mechanically support the electronics to keep everything in place during launch. Packaging this all in a fuse this small in the 1940s was no easy feat. The tubes manufactured for the proximity fuse were drastically smaller than existing conventional tubes. This, of course, helped immensely with resisting the force of launch. With 20,000 Gs of acceleration, Every extra gram of weight saving makes the difference. With this multiplication of mass, a single gram would weigh 20 kilograms. The engineering challenge of ensuring every gram of mass inside this fuse was supported by a structure capable of bearing 20 kilograms was immense. A challenge that deterred both the British and Germans, and its success drastically changed the face of the battlefield. The impact this fuse had on the war cannot be overstated. The atomic bomb was the punctuation mark of this worldwide war. But the statistics back the VT fuse as the most impactful invention of the war, an invention that changed the narrative of the war completely, a counter to the newly invented airplane, causing havoc across every theater of the war. Such importance was put on this invention that it was classified as top secret and only approved for use in the Pacific, where any unexploded rounds would be lost to sea. Much of the manufacturing was performed in smaller sub-assemblies to minimize any knowledgeable manufacturer from deducing the purpose of the device. And for good reason. During the London Blitz, it's estimated that 1,800 rounds were needed to take down a single aircraft. But with the introduction of the VT fuse, this number lowered to an average of 85 to 100 rounds, a 10 to 20 times increase in lethality. A jump in lethality that great is akin to the introduction of the machine gun. This was, beyond a doubt, a game-changing invention. At the peak of their production, over 250,000 of these fuses were being manufactured a week. The VT fuse was first fired on January 4, 1943, on board the cruiser Helena, defending itself from an aerial assault and successfully shooting the aircraft down. This device had a devastating effect on the aerial battles of the Pacific. Japan soon began to run low on trained pilots, and a year later began the kamikaze campaign, sending waves of untrained pilots towards American ships in the hopes just one could get through. In May 1945, 2 destroyers off Okinawa found themselves the targets of 150 kamikaze aircraft. Every single one of them was shot down, a feat that could not have been achieved without the radio proximity fuse, allowing the guns of these boats to fire relentlessly with accurate fire with no pauses to fiddle with mechanically timed fuses. Had the VT fuse been available during the Battle of Britain, the battle would have been even shorter-lived, with the anti-aircraft guns of London suddenly becoming an order of magnitude more effective. The swarms of the Luftwaffe bombers would have stood little chance of returning home. It was finally approved for use over land for the first time in conjunction with the Allied invasion of Normandy, a week before Germany began bombarding Britain with the V-1 buzz bomb. At its peak, 100 V-1s were launched towards Britain, and with the help of the VT fuse, 80% of these automated missiles were shot down. The VT fuse also played a pivotal role in the Battle of the Bulge, allowing artillery fire to explode at the perfect distance overhead, showering the canopy of the Ardennes forest with deadly shrapnel, repelling Germany's final large-scale counter-offensive of the war. Even at this stage of the war, with Germany on the retreat, the VT fuse was a closely guarded secret. Each and every fuse needed to be tracked and accounted for, with one story of artillery officers spending hours searching through snow to locate lost fuses during the Battle of the Bulge, only for them to be returned to them by locals.